On the morning of April 5, 1987, heavy snowmelt and rain forced Schoharie Creek to run higher than anyone driving over it had ever seen. The water churned violently just 10 feet below the rails of the York Thruway bridge. A tractor-trailer rolled west onto the bridge, and the road in front of the driver simply was not there. A 100-foot span dropped into the flood. Within minutes, 80 feet of interstate vanished, and 10 people died. Nothing that failed that morning was visible to anyone driving over it. The steel structure was sound, the concrete deck was solid, the paint was fresh, and the bridge carried its traffic without complaint. How does a piece of critical infrastructure with a clean inspection record give way with absolutely zero warning? The answer is that the destruction was assembling itself over 34 years in a blind spot. It worked entirely below the muddy surface, in a place no inspector ever looked and no driver could see. To understand what dismantled this crossing, you have to look at a mechanism responsible for the vast majority of bridge fatalities in the United States. That mechanism is a process called Scour. This chart breaks down the root causes of structural failures nationwide. As the data shows, Scour and hydraulic causes account for roughly 60% of all bridge collapses in the country, completely eclipsing material defects or vehicle collisions. Scour is the physical action of moving water encountering an obstacle. Instead of flowing smoothly around a pier, the current dives downward and digs into the riverbed. Bridges often fail because the very earth they stand on is quietly and continuously stolen away. After the collapse, engineers needed to interrogate a flood that had already drained away. At Colorado State University, investigators built a scale model of the bridge, running clear water over a sandbed to watch the physics in miniature. When a fast current hits a pier, it curls downward into a spinning horseshoe vortex. This vortex relentlessly lifts sand from the streambed, sweeping it downstream. Over time, this scooping action carves a massive hole, leaving the pier hanging over an empty void. In calm water, this process is slow, but in a severe flood, the river acts as a high-powered excavator, and no one above the surface can see it operating. To see how a modern interstate falls victim to this, we have to trace the timeline back 34 years. The root cause of the collapse sits on a drafting table in 1953. This cross-section compares anchoring choices. On the right, vertical piles driven into solid rock. On the left, cheaper spread footings resting directly on the streambed. Designers chose the footings, setting them into erodible sand, the exact material a vortex carries away. That decision might have worked for a quiet stream. But the Schoharie Creek had a documented temper, with major, violent floods recorded in 1832, in 1864, in 1869, 1879, and 1894. That history was sitting in the archives, but the designers never consulted it. They engineered a foundation for a tame, predictable waterway, placing massive concrete slabs in loose gravel directly in the path of a river known to rage. Even with a shallow foundation, the bridge had a second line of defense. The footings were ringed with riprap, large, heavy stones piled around the base to break up the vortex before it could dig. But a stone is only protection if the water cannot lift it. The specification called for stones weighing around 290 pounds. For this creek's natural flow, the rock needed to be 3 to 5 times heavier. The river began peeling the undersized armor away almost immediately. Decades later, a 1979 inspection clearly noted that the riprap had been displaced. The warning went into the file. Yet the engineer responsible inexplicably skipped taking dropline depth measurements, a simple weighted line that would have revealed the massive crater already forming beneath the piers. Then, during a 1982 rehabilitation project, 600 cubic yards of required replacement riprap were explicitly deleted from the final plans. Instead of restoring a compromised defense, deliberate administrative choices actively stripped the bridge of its armor right when decades of unseen erosion made it vital. By the spring of 1987, heavy snowmelt and nearly 6 inches of rainfall accelerated the creek into a 50-year flood event. Completely unhindered by any meaningful riprap, the horseshoe vortex tore into the bare footing of Pier 3. It excavated the bed materials so aggressively that up to 30 feet of the concrete column was left hanging over an open void. At 10:45, the support that was no longer there gave way. Pier 3 dropped straight down into its own scour hole. Because the bridge was a simple span structure with only 2 steel girders, it lacked structural redundancy. When one pier failed, the surrounding elements had no reserve strength to carry the newly unsupported weight. Span after span washed out in a rapid chain reaction. The catastrophe was 34 years of slow, unmeasured subtraction that finally surfaced as 90 seconds of total collapse. The National Transportation Safety Board's final conclusion was strict. There was no exotic material defect here, and no unforeseeable act of God. The investigation determined that if the required riprap had simply been maintained, the bridge likely would have survived. The 1987 river was no stronger than previous floods. The structure was simply undefended. Schoharie Creek exposed a blind spot spanning the entire country. Thousands of bridges built in the same era stood on the same shallow footings, protected by stone no one had bothered to verify against the local currents. It took the loss of 10 lives to force a nation to drag an engineering flaw out of the water and into the light. The failure at Schoharie Creek forced a total overhaul of bridge inspection protocols across the United States. The federal government issued a new standard known as HEC 18. It formally identified Scour as a primary, invisible enemy and mandated that engineers deliberately hunt for it. Passive observation from the riverbank was no longer acceptable. Modern oversight now requires active underwater verification, replacing assumptions with routine dropline measurements and specialized dive teams. Structural integrity depends as much on the relentless interrogation of the voids beneath the water as it does on the strength of the steel we build in the sky.